All right, before we get going, let's do a little bit of review about what we talked about yesterday. I gave you a few hints when you're doing redox chemistry. The first thing is treat individual elements as neutral, including if you've got two of them. So for example, O2, we treat as a neutral atom. Any other atoms that you see, treat them as ionic. If you're going more positive, that means you're losing electrons and being oxidized. If you're getting more negative, that means you're going in the reduction direction. We saw a few examples yesterday. We started off with some easy ones. So the first one, we saw iron is neutral when it's by itself, but when it's bonded to other types of elements, we know that in this case it would be 3+. That means each iron lost 3 electrons and was oxidized. Versus the oxygen went from oxygen O2 being neutral to oxygen 2-. That means it gained 2 electrons and was reduced. So today we're going to kind of talk about this in more detail and add in a few new terms. But let's briefly write down what we learned yesterday. When you lose electrons, is that an oxidation or a reduction? Who remembers? Oxidation. And if you gain electrons, that's going to be a reduction. So that's the most important thing we learned yesterday. However, today we're going to start talking about oxidizing agents and reducing agents, which are slightly different. So let's start out with oxidizing agents. And an oxidizing agent is a reactant that oxidizes something else. All right, another way of thinking about this is that if it's oxidizing something else, it must be taking electrons, right? So it takes electrons from the element that is being oxidized. All right, now the weird twist on this, right? So if an oxidizing agent is taking electrons from another element that's being oxidized, is the oxidizing agent getting oxidized or reduced? Right? It's taking an electron from something else. That means it's gaining electrons. That means the oxidizing agent gets reduced in the reaction. Say gain electrons. Does that make sense? It's the number one thing that students struggle with is this idea that an oxidizing agent gets reduced in the overall reaction. It doesn't seem to make a lot of intuitive sense, but if you boil it down to the main concept, if it's taking an electron from the thing being oxidized, it must be getting reduced. All right, we can do the same thing with reducing agents. And it is a reactant that reduces something else. And just like with oxidizing agents, in this example, if it's a reducing agent, it's not taking electron, instead it's giving electrons. And just like we saw with oxidizing agents, the opposite is true. So a reducing agent actually gets oxidized during the reaction. Because it's losing electrons and giving it to something else. Does that make sense? It's a little bit confusing. I will make a note too. An oxidizing or reducing agent is an entire compound. When we were looking at redox chemistry yesterday, we were talking about individual atoms being oxidized or reduced, but when we're talking about oxidizing agent or reducing agents, we're talking about the overall compound. So there may be multiple atoms involved there. So let's take a few examples and we'll practice this. And just like yesterday, I want us to first identify which atoms are being oxidized or reduced, and then we also want to identify which compounds are the oxidizing agent or reducing agent. So we're going to take tin oxide, react it with hydrogen gas to give us tin and water. So I'll give you some time to work on this, but first identify the elements being oxidized or reduced. I'll give you a hint too in case you're struggling with the tin oxide. A lot of students will look at tin, I'll say SN. If you look at the column that it's in column 4A. It's not immediately clear what charge that would have. However, what's the charge going to be for oxygen? Yeah, oxygen's always going to be -2, or 2 negative, I should say. Which means that the tin has to be what? 2 positive, exactly. So if you ever are in a pinch, just look at the other elements and make sure that you balance out the charges. Let's kind of walk through this just slowly. So we've already identified the charge for the tin. We've identified the charge for the oxygen. What about the charge for this hydrogen? Neutral. Right, because it's just made up of hydrogen atoms, we consider it neutral. And then if we think about the tin over here, what would this be? Neutral. All right, and then we can also think about the hydrogen over here. What would this hydrogen be? And remember, we're treating everything as ionic. Well, no, what charge would the hydrogen have? So hydrogen's in group 1A, that means we normally treat it as 1+, right? Okay, so if it's ionic, we treat it as 1+. And then last but not least, we've got this oxygen. If we think about oxygen, if we treat oxygen as ionic, what should it be? 2 negative. Okay? So now let's go ahead and take a look at our oxygen, for example. So it started out 2 negative, ending up 2 negative. Was there any redox chemistry occurring here? No. No electrons were transferred. So I'm just going to erase this and say it's really not doing anything interesting here. Looks like the tin and the hydrogen are doing everything important. Okay, so let's focus on the tin now. Whoops. Looks like we're going from tin 2+ to neutral tin. So are we gaining or losing electrons? Yeah, it looks like we're losing or gaining, sorry. Gaining. So each is gaining 2 electrons. Does that mean it's being oxidized or reduced? Reduced, exactly. So the tin atoms are being reduced. That's important to remember. All right, now we can do the same thing down here with hydrogen. Looks like hydrogen went from neutral to positive. Did it gain or lose an electron? Lost, right? It's going more positive. If we're going more positive, that means we're losing something with a negative charge. So each hydrogen lost 1 electron. That means that hydrogen is oxidized. All right, so we can highlight that. So This is what we did yesterday. We practiced identifying elements being oxidized or reduced. But now let's identify our reducing agent. Oops. Which is an entire compound, and our oxidizing agent. So what's the reducing agent? What do you think?
The hydrogen.
The hydrogen, exactly. If we look at the hydrogen, it's getting oxidized, which means H2 must be the reducing agent, right? So in this case, we'd say H2 would be our reducing agent because it's getting oxidized in the reaction. The oxidizing agent, on the other hand, must get reduced in the reaction. So this would be our tin oxide. This is different, though, when we ask what's oxidized. When we think about what's oxidized, we're just thinking about individual atoms. So when we think about oxidation, focus on individual atoms, which in this case would be a hydrogen atom. And reduced wouldn't be the tin oxide, it would just be the tin, because we know the oxygen wasn't reduced in the overall reaction. Yep?
For the reducing agent and the oxidizing agent, is it always going to be, in this case, on the right side of the equation?
Yes, it's always going to be, or sorry, the left-hand side of the equation. It's going to be on the starting material side. Yeah, your other right. So the oxidizing agents and reducing agents, that's actually a good note, are always entire compounds and on the left. These down here, what's being oxidized and reduced is individual elements. Make sense? All right, let's do a few more practice ones, just because I know this is confusing. And in this next practice one, we've got V2O5, looks like vanadium oxide, plus hydrogen, goes to V2O3, plus water. First thing I would do is balance it, and then what I would do is try to identify individual atoms that were oxidized or reduced, and then I would determine what's the oxidizing agent and which is the reducing agent. So I'll give you a little bit of time to look at this. Who needs help finding the charge for the vanadium, the V? Maybe a few people. I'll show you my trick for determining charge. The problem with vanadium is it's a transition metal. We don't know the charge right away, right? But let's take this one, for example. It's V2O5. So we know we have 2 vanadium atoms, and we've got 5 oxygens. So 5 oxygens. We don't know the charges for the vanadiums because they're transition metals, but we do know that transition metals are always cations. So I'll just write question mark plus. What about oxygen? What charge does oxygen have? 2. 2 negative. So if we look at all of these together, the net charge for all of the oxygens is -10, right? Which means the vanadium atoms must have what charge? 5 plus, exactly. So you can use tricks like this to determine what the charge is going to be for your individual atoms, and you may need to do the same thing for V2O3. So I'm going to leave this up here just in case you want to take a note. All right, so we worked through the vanadium 5 oxide. We knew that the charge for the vanadium had to be 5 positive, and the charge for each of the oxygens was 2 negative. What about the hydrogen? It's H2. Neutral, exactly. All right, now we'll go over here. What will the charge be for this vanadium? Yeah, positive 3. If you do that same trick, in order to have canceling out charges, each of these vanadiums would be 3 positive. All right, what about the oxygens? Exactly, each of these oxygens would be 2 minus. Now we can go over here to this hydrogen. What would this hydrogen be now that it's not by itself? H plus, exactly. All right, and then what about this oxygen over here? No change, right? It's going to be considered ionic. One thing I'm noticing here is we've got oxygen with the 2 minus, oxygen with the 2 minus, oxygen with the 2 minus. It doesn't look like anything's happening with the oxygens. They're not gaining or losing electrons. So I'm just going to go ahead and erase this just to make things clear. Looks like all of the electron transferring is either between the vanadiums or the hydrogens. Okay, so let's do vanadium first. Is vanadium gaining or losing electrons? Yeah, it looks like it's gaining electrons. It's becoming a little less positive, so it must be gaining electrons. So I'd write down each vanadium gained 2 electrons. So was it oxidized or reduced? Reduced. Okay, and then up here we can do the same thing. It looks to me like each of the hydrogens lost an electron. That means that hydrogen was oxidized. Does that make sense? You always have this combo of something being oxidized and something being reduced. All right, now we've got to consider our reducing agent and our oxidizing agent. And what do you think the reducing agent is going to be? Yeah, it would have to be the H2, right? Because the hydrogens are being oxidized in the H2. That means H2 must be the reducing agent. And the oxidizing agent in this case must be the other component, which would be the V2O5. And then when we ask what is reduced, we said previously that it was an individual element. Specifically, it's going to be vanadium. And then what is oxidized? It must be the hydrogen elements, right? Does that make sense? Yeah. Yeah, if we think about the agents, they must be entire compounds, right? So each of these two are entire compounds on the left-hand side of the chemical equation. And then what we could do is look at the hydrogen, right? We said each hydrogen was oxidized. That means H2 as a compound must have been the reducing agent. So it's always going to be the opposite, if that makes sense. How many of you want to try another one of these? All right, that's good. We'll do another one.
The whole class.
The whole class. Because I know everybody comes out of the womb knowing how to do this. Yeah.
Can we do one that's kind of like the last one from the pod, where it's like a molecule with 3 elements in it?
Yeah. In fact, let's the pod, because why not? All right, so this one's a little bit tricky. Let's consider all of these hydrogens. What charge will hydrogen always have? +1. And what charge will oxygen always have? 2 minus. All right, now we've got some funky math to do. We've got 12 positive charges, right? So if we look at the net charge for all of these hydrogens, it's going to be 12 plus. Whoops, that's not a 12, that's a 21. So we've got a 12 plus, and then over here with the oxygens, what charge do we have? Total? 12 minus. All right, which means that this carbon is going to be considered what? Neutral, right? Because we already have canceled out all of our charges. All right, so we've got this carbon that's neutral. Now let's look at the carbon on the right-hand side. Question is, well, what charge would this have? In order to do this, we need to first remember that the charge for each oxygen is going to be O2 negative. Whoops. times 2 oxygens, which means we've got an overall charge of 4 negative, right? Which means the carbon for CO2 would have what charge? 4 plus. All right, so this would be carbon 4 plus. So you can use that trick as well if you're running into some of these complicated molecules. All right, so I'm just going to erase this up here. If we think about neutral carbon going to carbon 4 plus, is it gaining or losing electrons? Losing electrons. So in this case, we could say carbon was oxidized. It lost electrons. Does that make sense? All right, now let's take a look at the oxygen over here. This oxygen must be what? Neutral. Okay, and then we've got oxygens in both CO2 and H2O. What charges would they have in either of those? 2 minus, exactly. So over here, I'm just going to pick one of them and say this is going to O2 minus. Okay, so when we look at oxygen, did it gain or lose electrons? Okay, so oxygen is reduced because it gained electrons. So I'm going to go ahead and highlight these just so I can focus on my end result here. Yep.
Is it really some of the oxygen reduced though?
Yeah, it's interesting because if you look at, let's say, these oxygens, these were O2 negative. So these oxygens in C6H12O6 didn't actually gain or lose any electrons. It was only the oxygens from O2 that gained or lost electrons. Great question.
How do you know where they go? Like, which ones?
We're not going to get super far into that. You can start bouncing them if you go on into general chemistry. Right now, this was more of a challenging one where I wanted you just to keep track of, all right, which elements are gaining or losing electrons. Okay, so now we've got our tricky thing. We already identified the atoms getting oxidized or reduced, but now we've got to identify our reducing agent. What do you think our reducing agent is going to be? Yeah, the first compound, exactly, because it's got the element in it, that carbon, which was oxidized. So it must be our reducing agent. So it'd be C6H12O6. There we go. And then we can go ahead and we can say, all right, we've got an oxidizing agent. And what would the oxidizing agent be? O2. Right, it's always going to be the starting material of compounds. Yep.
So would the proper answer be 602 or O2? So it basically does it have to be balanced, or are we just going down to the most basic?
We're going down to the most basic. If you did 602, I'd give you full credit, though. It doesn't bother me. Makes sense? Some of these are a little bit complicated, but like I said, try to break everything down into ionic components. And then if you have any leftovers, try to bounce the charge and predict what it might be. Carbon is really hard to predict the charge. And we talked about this briefly before where I said carbon has 4 valence electrons. So it has a few options to fulfill its octet, right? It can either gain 4 electrons or lose 4 electrons. Doesn't really have a strong preference either way. So its charge can vary wildly. You'll see this a lot in biology. Oxidation chemistry is very important for cell metabolism, specifically in mitochondria. Does this make sense? Hopefully this will avoid a rush at office hours tomorrow for that last one. Do you want to do any more? Raise your hand if you want to do another one of these. All right, we'll do another one. All right, let's do... Let's do just a simple one at first, and then we'll switch to the one we saw in lab. So let's do another simple one just to practice. So we've got potassium plus elemental bromine goes to potassium bromide. In order to bounce this, we would have to have a 2 here to bounce out the bromines. And we doubled our potassium, so I got to put a 2 over here. Okay, so identify what was oxidized, what was reduced, and what your oxidizing agent is versus your reducing agent. All right, let's try to do some of these slowly and walk through this problem solving. So we'll start with potassium on the left-hand side. It's one of our reagents. What charge would this be? Neutral. Perfect. All right, and then we'll switch over to the potassium on the product side. What charge would this have? +1. It's in group 1A, so I'll just write K+. And if we think about potassium here, did it gain or lose electrons? So if you gain electrons, you should be getting more negative because each electron's negative. So in this case, it's the opposite, right? We're getting more positive, so it'd have to be loss of an electron. So each potassium lost 1 electron. So is it being oxidized or reduced? Oxidized. All right, so we've got half of the job done. Got to do the other half now. If we think about bromine here, would this be neutral or 2 negative or 1 negative? Neutral. It's by itself. And then bromine over here, what charge would bromine have as an ionic compound? -1. So really quickly, we can say each bromine gained 1 electron because we know it's getting more negative. That means that bromine was reduced. Okay, so now we've identified the atoms or elements being oxidized or reduced. Last thing we want to do is identify our reducing agent and our oxidizing agent, which is different than the individual elements being oxidized or reduced. What's our reducing agent? So if you remember, your reducing agent should have the element that was oxidized in it. So in this case, the reducing agent would actually just be potassium. So in this case, potassium's both being oxidized and acting as the reducing agent. All right, that means our oxidizing agent must be Br2. The entire thing, not just one of the bromines. Does that make sense? These do get a little bit confusing. All right, let's take a look at an example from lab. This was a few weeks ago when we did the battery lab. All right, and in lab, what you had was you had a zinc strip. And the zinc, because it's a solid, we put in parentheses behind it S. That just indicates that it's not dissolved, it's just solid metal zinc. And we put this into a solution with a bunch of copper cations. That was our copper sulfate solution. So that was copper 2+. And in order to indicate that it's in water, we write AQ for aqueous. It just means it was dissolved in water, not in an alcohol or something else. And during this reaction, if you remember, the zinc started having this film grow on it. That was actually copper being formed. So if you left it in there long enough, you might have actually noticed that copper color starting to form. And when you do this, you actually create zinc cations that go out into solution and are colorless. All right? So let's identify what was oxidized and what was reduced in this reaction, and what was the reducing agent and the oxidizing agent. actually going to delete that picture and show a different one. If you think you got this, give me a thumbs up too. A few thumbs. All right, let's try to do this together. So for example, zinc here, is that going to be positive, negative, neutral? What charge would it have? Neutral. It's just a metal. And then if we think about zinc over here, whoops, forgot my L. It's already given the charge, so we know it must be zinc 2 plus. So if we think about this, was zinc oxidized or reduced? Oxidized. It lost 2 electrons. So zinc lost 2 electrons. Zinc was oxidized. So that's pretty straight. Whoa, that's not what I wanted. So that one's pretty straightforward. So I'll just highlight this so we can keep track of things clearly. Now we'll focus on the copper. Intuitively, we know it must be reduced because it's got to match that oxidation. But up here, we went from copper 2 plus to copper that was neutral. And you can see that the copper, in this case, gained 2 electrons. That means copper was reduced. So I'll just highlight this for the time being. All right, so this was a cool experiment that you did in lab. One thing I think it asked in the post-lab that we never actually completed was what would happen to the color of the solution over time, and this actually shows what happens. So that copper 2 plus solution was originally brilliant blue, and then over time, if you look at the zinc metal, it's a little hard to see on the screen, zoom in more. It starts out looking a little rough, and then it starts having these ragged edges and big spikes growing off of it. What do you think those big spikes are? So what's the stuff growing on the zinc? It's got to be the copper, right? So in this case, we'll make a note that copper is growing on the zinc. So copper metal forms on zinc. And we can tell that from the overall redox reaction, right? Because in the redox reaction, when all the electrons are transferred, we're actually forming copper metal. The other thing you may notice too is this color of the solution. It started out a brilliant blue, almost like a royal blue, and over the span of the experiment, it got lighter and lighter and lighter, and eventually it would be colorless. Why is that? What do you think?
Because the zinc electrons are pulling the copper electrons out of the solution and forming on the zinc, which leaves the clear liquid. I don't have to form in front of it, I'll make water.
Yeah, exactly. So when we're looking at this reaction, the blue is actually due to the copper 2 plus cations, right? So the copper 2 plus cations are that brilliant blue. If we're pulling all of that copper out of solution and turning it into a metal, there's no more blue left, right? So that color disappears. The zinc 2 plus cations that we're forming on the right-hand side don't have any color, so they don't change the color in any way, shape, or form. So the solution just goes to clear. Does that make sense? All right. I think I'm going to leave it at that today. Tomorrow, when we come in, we'll start to relate this to batteries, but I would encourage you to start looking at that problem of the day and try to complete the remaining 2 problems.
What would be the agent?